Welcome, physics students, to the first online lecture of the year. I'm excited to be working with you in this way and hope you enjoy these series of lectures that you're going to get this year. Today's lesson is on mathematical models for linear relationships. Now, we're going to continue on with our variables talk from last week, and we're going to also access some information you already know from your math classes. And so this is hopefully a review for you, and we'll do a couple examples to get you through this. And on Monday, when you get to class, or whatever day you come, we'll then go ahead and start trying these on the worksheets and start working through these things next week. So a mathematical model. So a mathematical model is an equation involving the independent and dependent variables, just like we talked about last week. The independent, dependent. Now we're going to focus on graphing them to come up with equations. Lines on a graph, an area underneath a line, may describe an equation, or what I'll call a mathematical model. That is all that is, just an equation. It just represents a line. Okay, so for example, here's a linear line on a graph, and it shows you have your y over here, your dependent and your independent variable on this axis. All right? So this data can be fit by a line. And the equation for the line is y is equal to mx plus b. Now, I know what you're thinking. This sounds like a lot like math class. Well, it is a lot like math classes. The only reason that math does these things is so that we can understand things like lines in physics and lines and trends in economics. That's the main reason we learn to do those things. Okay, so this line is some sort of y is equal to mx plus b, like it said in the other slope, or in the other slide there. All right, so let's just go ahead and review your mathematics now. So y is your dependent variable, and it can be replaced by the name of the variable that's graphed on the y-axis. Now that's new. In math, very few teachers will have you substitute other names in for y. But we talked about that yesterday. It's just kind of the generic version of it. X is the independent variable, and it can be replaced by the name of the variable that's graphed on the x-axis. Okay, you don't do that in math, but we're just going to continue on. You're learning your information. We're going to go on with that. Okay, m represents the slope and can be calculated by taking delta y over delta x, or the change in dependent divided by the change in the independent variable. Some say it like this: rise over run. Make sure you get that in your notes. That's how you calculate your slope. If you go back to the graph, it's how far up divided by how far over it goes. You take those two numbers, and that gives you your slope. And then, of course, we have the slope. And then we have, so the slope by definition is the ratio of change between the two variables. How much the dependent variable changes as the independent variable changes. Delta y divided by delta x. B in that equation is your y-intercept, and it's written as a unit of measurement. Okay? And so we're going to put that together now. We'll put that all together in just a second. So, but first, before we go into substituting that, let's go ahead and calculate the slope of this line. And go ahead and try that again. So rise over run, or delta y over delta x, which is y2 minus y1 divided by x2 minus x1. Again, that is review. If you have trouble with that, or somehow you missed that in math, talk to me on Monday and we'll go over that in more in detail. So what we have here is it goes up, starts at 10, ends at 60. So it rises 50, and it goes over 6. So some people want to say 60 divided by 6. You got to be careful. It's actually 50 divided by 6 in this situation. So what we have here, it goes up 50, and we want to put a units on that, so that's 50 meters in 6 seconds. Now, we don't leave them as fractions. In science, we always go ahead and calculate those things through. So I'm going to go ahead and do that. So the solution is 8.33 meters per second. And I round that number off. And we'll learn about rounding off in significant figures maybe later this year. But go ahead and just round that off. If significant figures, we'll worry about those later on this year. I want you to learn about this stuff first. So let's go ahead and substitute in the variables. Now, so let's go ahead. So a lot of you aren't going to get this at first because you don't want to switch from y equals mx plus b. So let's first look at the y-axis. So the y-axis name is position, so we'll substitute that name in for y. The x-axis name is t, or time, so we'll substitute that in there. Many of you will, again, have trouble. The concept's not hard, just the format that I use is going to be different for you. So we'll go ahead and substitute in here position equals our slope, so we'll put our slope in there, 8.33 meters per second. Then we'll put in our x variable, which is time, put a t there, and then we need to find our y-intercept. So to find our y-intercept, you just come over here, and our y-intercept is right here. It's the value of y when x is equal to 0. So check this out. So here's 0. Just come up here, and this is where it crosses. So that's where it crosses. So it's 10. It doesn't matter if its name is position or y. It's the same thing. So it's the value of, it's 10 there, 10 meters. And don't forget your unit on there. So come over here, plus 10 meters like so. So anyway, sorry about that. It doesn't quite line up, but that'll work. So there's your B right in there. All right. Well, let's continue on. So state this relationship in words. So the position of the object in words, it says, I would say it like this. The position of the object is 10 meters at time equals 0 seconds. And it increases, and position, I'd put in there, increases 8.33 meters every 1 second. And so you just use the slope. So you know that, you kind of know what the rate of the speed is then, because it goes 8.33 meters every second. So, all right. Again, we already kind of covered this. What's the value of the y-intercept, and what does it mean? The y-intercept is the value of y when x equals 0. In this case, it's the value of position. I don't know what's wrong with my marker here. Let me fix that. So specifically in this situation, it's the value of y when x equals 0. Or not in this situation. So you always, when you're doing these, it always starts as this. That's your mathematical definition. Now just substitute in your values. So it's the value of position when time equals 0. And you can do that with any situation. Doesn't matter what the two variables are. It's always that. Okay, so let's apply this to a problem. Now you can take your equation and solve a problem with it. So the previous graph explains Jordan's motion while flying a kite. After Jordan has flown his kite for 20 seconds, what is his position? So you're trying to find position. Your time is equal to 20 seconds. And your equation is P is equal to 8.33 meters per second times time plus 10 meters. So all we have to do is take that 20 and plug it into our formula we used, and that'll give us our solution. So you just take 8.33 times 20 seconds plus 10 meters. So its position ends up being 176.6 meters. And make sure you include the unit. The other format is, when I go through these, is when you write out your equation, this has no units, this has units, no, yes, no units, yes units. And that's going to get a little bit tricky. Again, it's a format thing that I'm going to be real strict on. So most of you understand the concept. This is not the first time you've seen this, but it's going to be my specific format that gets you in trouble. All right, so now I'm going to go ahead and switch to part 2 and go ahead and watch lesson 1, video 2, and we're going to do an example problem that's going to be like one we go through in class.